and it's going to participate in the competition in May, I believe, with real robots, and the competition itself will be held in China, I believe, again. So there's a pretty new team, and there are people that were doing computer vision and control during the summer internship last year. And during the autumn, we were talking about computer vision in greater detail. And now we are dealing with the control. Control, I mean, not management, but control of the dynamical systems, like control theory, that kind of thing. And we are basically talking in great detail about small systems that, however, show the basic properties and the basic behavior of the real robots. So I'm going to say a couple of words about the models that we use. Let's say that we have a humanoid robot, and I will draw it like a child. I'm really not a designer myself, so this is the robot. We are not going to consider its hands or head or whatever. So it's just a point mass, and it's on a flat terrain. So we really consider these robots, or even if the robot has all those details, we will disregard them. And instead of the full model, we're going to consider a system consisting of only a point mass. Both of them are in the gravitational field. And this is an object that is called inverted pendulum. So the equations of motion of this thing are, I think, familiar to you from the high school. So they're much simpler than the equations of motion of this big boy. And last time we were talking about so-called Lagrangian formalism, which is a way to obtain the equations of motion, the differential equations of motion of certain mechanical systems. If something is not clear, that's my fault, so please tell me about that. I will correct myself. And the home assignment was to find out the equations of motion of such a system. There's a flat frictionless surface, mass m, and spring with a stiffness k. So do you have an idea what the equations of motion should be here?
I guess they have to be like F is equal to minus kx is equal to the mass times acceleration of the block. But
yeah, right, that's true. So you know the system already, and we're going to go through the Lagrangian formalism that I have mentioned, which will allow us to obtain the equations of motion for much more complex systems when we cannot really just observe the system and get the equations of motion. For example, there is another very classical system which is called cart pole. It consists of a cart on a rod and a pendulum, inverted pendulum with different masses. Have you seen this one previously?
I do not believe I have.
Okay, no problem. So the difficulty that we have here is that we can apply forces to this block, to this cart, but this joint is passive, so we cannot act upon this pendulum. It's just hanging. So if this is a cart and this is a pole, the pole being displaced just with a slight angle, say to the right, it will swing down if we will not control the whole system properly. And the upright position of the cart or of the pole here is an unstable equilibrium. So we have to come up with a certain policy to control the system to be upright. And you can ask, what's the point? Why do we even need that? Well, the thing is that we can represent certain dynamical systems of very high dimensionality using those simplified models. So the idea goes as follows. There's a full humanoid, like 20 degrees of freedom, non-linear, very complicated stuff. We simplify it. Oh, hi, Nasiba. Good afternoon. We simplify the system more and more so that it starts resembling something that we can deal with. And after that, we can apply all those techniques that we have developed for the simple systems while considering all the extra stuff as disturbances, noise, and so on. So we're acting like the robot is a pendulum and the rest is just noise for us. So that's the plan.
I see. Okay. So we're breaking down the bigger problem into smaller problems which that we know how to solve, essentially.
Yes, that's true. So we have a full robot. Let me show it. This robot has 20 degrees of freedom, meaning that it has 20 controllable motors, controllable by position. We cannot really get any complete analytical solution for the trajectory of this robot. If we want this robot to go somewhere, we cannot obtain, we cannot solve equations that will provide us with the optimal solution. Why so? Because there are too many variables, too many unknowns. We cannot go beyond polynomials of order 5. We cannot solve them in general case. And here we deal with the problems that are called non-convex. So they're very difficult to solve. The systems are noisy. They deal with the real world, real sensors, delays, and so on. So the problem is very complex, and we cannot consider it in its entirety. So we try to boil it down to simpler cases, like, say, this thing. And how does the robot resemble cart pole? Well, basically, robot has 2 feet, and if someone is pushing us from the back, we can step just further. So this catching footstep will provide some kind of motion that will catch the mass. That's the idea, the rough idea. But really, there is nothing more than trying to stabilize certain systems in non-stable equilibrium points. By the way, Nasiba has joined us. Nasiba has been attending our seminars for a long time already, so you can ask her about what's going on with the course, with the robots, and so on. So you can talk between yourself. I mean, I'm not even a student, so I don't know the context.
Hi guys, feel free to text me. Also, Nakia has my number, so Neyman, if you have any questions, we'll ask.
Yeah, sure. Thank you so much.
No problem.
Yeah, there are also other students. You can text them in WhatsApp, or you can text me. I don't remember if I have my name in English in WhatsApp. I believe I do. So you can, I'm the guy who's sending the links. You can text me anything if you want to ask anything. Yep. So Lagrangian formalism. What is that? I'm going to briefly remind you of what was going on during the last lecture, but if something is not clear, let's go over that again. So for this system, we can define both kinetic and potential energies. How can we do that? Well, our state vector x, it's the thing that is describing the state of the system, basically. It will consist of x, the coordinate, not the vector, and x dot, which is the time derivative.
So the velocity.
Yes, yeah, exactly. It's v, it's the same thing as the time derivative, and it's dx by dt. So in such a case, the kinetic energy is simply m x dot square over 2, and the potential energy, well, I'm going to move 0 right here, where the equilibrium of the spring belongs to, just to make everything simpler. If our block is sitting in 0, there is no force from the spring acting upon it. I can really move my system of coordinates anywhere, there's no problem with that, but the equations will look nicer. So the potential energy, that is traditionally denoted by T for some reason, will be k x square over 2, where x is just the displacement relative to the 0 position. This is just a normal spring with Hooke's law, and this is the kinetic energy. And the core idea of the Lagrangian formalism is to catch the flow of energy from the kinetic to potential. So we are defining so-called Lagrangian. Lagrangian is a function that is equal to the difference between kinetic energy and potential. So kinetic minus potential. It could seem counterintuitive at first. We are used to adding them to obtain the whole energy of the system, the total energy. But Lagrangian works this way, so I'm not going to prove that. That requires variational calculus and some just purely mathematical tricks. And we are going to talk about the ways to use that to describe our systems, because basically, what do we want to do with the system? We want to describe it so that we understand the states that this system could have, and we would like to understand the ways in which the system evolves. So how do the states transfer to different states? And since we are concerned with dynamical systems, naturally, we come to the notion of differential equations that describe the behavior of the system. So the next part is, it's in the frame. So the next thing that is going to be said is a bit difficult, but the thing is that it's the most difficult part of all of that. The rest will be simpler, and it will be fine after second, third time of you using that. So I have mentioned that the whole description of the system is a two-dimensional vector, x and x dot. And here, the system has 1 degree of freedom in the sense that in terms of the displacement, this block could move only to the left and to the right along one axis. So we, as roboticists, will call this 1 degree of freedom, 1 degree of freedom. And for each degree of freedom, in the standard case, there will be just the coordinate and the velocity along this degree of freedom. So if we are talking about linear coordinates, it will be just the displacement and the velocity. If we're talking about rotational motion, it will be the angle and the angular velocity. But they are really the same, because the tensor of inertia is really just like the mass, but just weird mass. So Euler-Lagrange equations. these are exactly the equations that are interested in. So the thing, the Lagrangian, and these equations will basically give us the differential equations describing the behavior of the system. That's the very foundational idea. So does it make sense what is going on or not really?
So we use these Euler Lagrange equations to describe how the position and the velocity, basically the state of the system changes, essentially.
Yes, exactly. So
Derive-
you have correctly guessed that we will get something along the lines of M A is equal to minus KX. Yeah, right. So it's the same as saying that MX double dot is equal to minus KX. But this is from observing the system, knowing the intuition, how the springs works, and so on. And we are going to use this simple system to get the intuition of how to use this apparatus to obtain the same result. So yeah, about these equations, you're right, and we're going to obtain them using the Euler-Lagrange formulation. So I'm going to say that we have a number of generalized coordinates, and the coordinate number I, the generalized coordinate number I, will be called Qi. It's the traditional notation. In our case, we will have our I running just from 1 to 1 because we have just one generalized coordinate, it's X. But for systems with higher dimensionality, it will be 1, 2, 1 to 3, and so on. So I goes over 1 through let's call it D. D will be the dimensionality. So in our case, D is equal to just 1. And we will have just Q1, which will be really X. And now the equation itself. So given the Lagrangian, I'm stating that for each of the generalized coordinates, the following partial differential equation is going to hold. D by dt, excuse me, of dl by dq dot minus dl by dq is equal to 0. This is the Euler-Lagrange equation, q sub I, excuse me, q sub I, and here q sub I again. So here I will go through all the possible values, and for a system with d dimensions, with d degrees of freedom, we will get d differential equations that will describe the behavior of the system. Let's catch up on that. Are we happy?
Yeah. And so what are we taking considering as L here? And in this case, we are taking X, Q as like X. But
Yes, and L is the Lagrangian.
okay. Yeah.
Yes, that's the point. So why do we even need that? We can observe the system and write down the differential equations. So why do we have to bother with this strange formulation? The point is that if we say want to describe the behavior of more complex system like this one, it will be much tougher to not to forget any link or joint or forces counteracting each other, because it's not quite clear what's going on. This pendulum is swinging, say, to the left, and the cart is moving to the right. There's also gravity. So I don't know. It's not that intuitive.
So in the
And
more complex, case, we take the Lagrangian in terms of like all the degrees of freedom, like x, y, like we calculate we find a formula like equation for the Lagrangian, and then we find three, or like if there are 2 degrees of freedom, we find 2 like partial differential equations corresponding to like
almost. So for 2 degrees of freedom, we'll get 2 ordinary differential equations that we will obtain with the help of this partial differential equation. Let me demonstrate this whole process until the end. So I'm going to just calculate this thing, then I'm going to differentiate it by time, then I'm going to calculate this one, and then we'll get the final differential equation. So it will be more clear. But yeah, you're right, except for one tiny detail. So let's do that. I'm going to write down the Lagrangian just directly. So it's m x dot square over 2 minus k x square over 2. The partial differential, the partial L, partial Q I dot, this differential, let me write it down, is d by dx dot of the Lagrangian, which is here. So I'm going to write it down. Mx dot square over 2 minus k x square over 2. I'm going to differentiate this Lagrangian by x dot. So let's find out what will happen. By the way, we are preparing for the competitions, for the competition in Taiwan in this moment, and there's a game being played, one against the goalpost, and there's my colleague Simon. He's a master student, so he's working. He's trying to fix this robot to work properly. This is how the robotic football looks like. The robot is kicking, but it could
that's
do
really
better.
cool.
Thanks. So we can check that closer, really. So hold on. Yeah, now the robot is going to kick the ball.
Nice.
Yeah, so we have the whole field in the lab. It's 6 by 9 meters. And the robots are supposed to play 4 against 4 here. We have the goalpost that is made of sanitary tube. You know, just the plastic tube, nothing more.
This is really
yeah,
like,
and
really cool.
also the robot is capable of standing up when it has fallen. So the plan is for your team to work with the same robots. And now we're talking about control. It's very, very distant from the real practice. The real practice will be delivered by Fedor, the other PhD student that I have mentioned previously. And I'm going into this from the theoretical perspective. And Fedor will give you the hands-on skills to tune the robots, to fix broken servo motors and all that stuff. Okay, let's get back to the Euler-Lagrange equations. Let's differentiate this Lagrangian by dx dot. Do you have difficulties with doing that? So if you do, there's no problem. I can just describe that.
So if we're differentiating, like, okay, first we are differentiating mx dot squared divided by 2 with x dot, right?
Yes,
So
exactly.
that would be like 2 times mx dot divided by 2. That's like mx double dot, right? 2 dots, because we are differentiating that again. So
You mean we differentiate that again? Okay. So let me just briefly remind you of the partial differentiation. In order for these x dots not to obstruct our vision, let's consider a function of two variables, x and y, and it will be equal to x squared plus y cubed. So partial f, partial x will be, what do you think? Okay,
just
so let me let me show you the example, and then we're going to use that to differentiate everything. So it will be just 2x because y doesn't depend, but this term doesn't depend on x. And in terms of x, it's just like a constant. So the partial derivative of this function by x is just 2x, and that's it. The same for y. But in this case, the multiplicative term here will be 3, and here will be y squared. So here, using basically this line, we can derive what we need. So the second term doesn't depend on x dot. Now we are considering x and x dot to be two independent variables. Why so? You can ask, why is that? It doesn't make sense because one is the derivative of the other. But the thing is that I can have velocity of 1 meter per second here, or I can have it here, or I can have it anywhere else. So in such a case, all the states could be reached by this system. And I can have any coordinate and any velocity. So they're independent.
okay, that makes sense. Yeah. And
so yeah, let's try once again to do this. What will be the result?
So would you erase the x term as a constant and just have mx, like mx dot as the differential?
Exactly. It will be m x dot. The second term doesn't depend on x dot. And here we have 2 that is canceling with the denominator. So yeah, exactly like this. We have calculated this thing. I'm going to take another marker. I have multiple. Okay, so we've got this one. And now let us cover the differential by time of this thing. So d by dt of partial L partial q sub I dot will be equal to this d by dt of m x dot. Right?
yes, okay, this makes a lot more sense. Yeah. And this is mx double dot. Yeah.
Exactly. Mx double dot. So now we've got the first term covered completely. Let us do the same for the second term. So partial Lagrangian, partial q sub I without dots, just the coordinate. It will be partial Lagrangian by dx. So let us check with the Lagrangian. What is going to be here?
And now we consider the mx squared as a constant, mx squared by 2 as the constant, because it's independent of x. And we
Yes.
just differentiate minus kx squared by 2, and we get minus kx.
Right. That is right. And now we have got this thing as well. So the only thing that is left is we have to construct this whole equation. We have to just stitch this part with this one. I'm going to move to the left. I'm going to remove this. And we are going to construct our beautiful differential equation that is describing the evolution of the system. So the first part is mx double dot minus the second part, which is minus kx. So it's plus kx, and it's equal to 0, which is equivalent to mx double dot is equal to minus kx, which is exactly what we have guessed over here. So the results match, and the most precious part here is you see that the battery has discharged, so it's beeping. It's creating awful noise for Simon to switch the battery. So the most precious thing is that it will keep working for more complicated systems, like say cart pole, so pendulum on a cart. And even if we consider some crazy system like pendulum like this, so there will be mass 1, length 1. Here will be mass 2, length 2. And here will be mass 3, length 3. It will still work. So there are proofs of that. They could be found in courses on theoretical mechanics or on differential equations, variational calculus, that kind of thing. So we're not going to cover the details of the proof, and I cannot really provide them at this moment. But we're going to use this as a tool to derive the differential equations of motion of certain systems. So are there any questions or difficulties with this one? What do you think?
None come to mind right now. Maybe another example.
Okay,
So far, yeah.
sure, let's do that. So let us dive into that, and let us consider a system with more degrees of freedom. So there will be a linear rod, and there will be some kind of fixed point, and there we will have a spring, and there we will have a pivot joint, and then here we're going to have a pendulum. So it's a pendulum on a spring. It's a crazy system, right? Because you can imagine the kind of behavior that you could expect. Let me find out an example. Hold on, I'm going to carry around something. Let me find one. Hold on. I'm here. I'm trying to find some example of the system. So something like this. There's a spring that can bounce, and there's a pendulum. So you can imagine the complex nature of the dynamical behavior of this system. And in contrast to the simple case of a one-dimensional pendulum, you cannot really think of the exact differential equations. They do not intuitively come to your mind. And we're going to use this Lagrangian formalism to derive the exact differential equations of motion of this system. And after that, we're going to simulate them using Python. Okay?
Okay.
So, by the way, are you familiar with Python?
Yes.
Great. So next time we'll simulate this thing, and we will change the parameters and just observe the behavior. It would be very nice. Mass, length, G, we have everything. Stiffness. Okay, and we are going to describe our system with a state vector. So how many variables do we need to describe this system? What do you think? How many degrees of freedom are there?
It can move up and down, and like the angle, I suppose, theta.
Right. So this thing is moving only up and down along this rod. So I'm going to call it the displacement and the angle theta. Right. So 2 degrees of freedom. And for each degree of freedom, we are considering it and its derivative, its time derivative. So the whole state vector will consist of d dot, theta dot. And this state vector lives in R4. Is it a familiar notion? It is, right?
Not really, but
Does that
Okay.
mean set of real numbers or something?
Yes,
like that?
yes, exactly. Those are real numbers. So this thing is a 4-dimensional vector. It adds like a vector, it multiplies like a vector, just vector.
okay.
And each of the elements of this vector is a real number. So let us just check. Yeah, 0 of this d will be somewhere here. And if the pendulum is swinging, is not swinging, if it's hanging down and nothing is moving anywhere, there's the zero. It will be just handy for us to do it like this. So yeah, and if say the direction of this axis will be it will be down. The angle is positive counterclockwise, so nothing special. Regular angle and linear displacement. Let us now find out the Lagrangian. It will be longer, and probably it will be more difficult to write it down exactly, but the thing is that we don't have to think about forces counteracting or whatever else. Can you imagine the pain of trying to write the equations of motion of this thing just from your head? Because there is a force that is acting on the rod, say to that direction. If something is spinning, it's acting on the hand that is spinning, and there is a normal counter force that is acting from the vertical rod. So the force to the right is being cancelled. However, the force down this rod is not being cancelled. So there are many things to consider, and we're going to use just the Lagrangian formalism. Instead of that, we're going to write the kinetic energy, the potential energy, and that's it. We'll be happy with that. So let's start with the kinetic energy. The kinetic energy of the system consists only of the kinetic energy of the mass, and it consists of, well, basically it's m/2 times the module of the velocity squared. I'm going to write it down like this. And let's find out what does this consist of. So there's clearly some horizontal velocity and there's some vertical velocity. And here they are squared. So I'm going to write it down like this. Vx squared plus Vy squared. And Vx squared, the horizontal one. By the way, how do you feel like deriving this yourself, or it would be better if I do it? What do you think?
I think you could help us out a bit with this one since we're still figuring out the equation.
Okay.
Yeah.
Okay, sure. So I'm going to do that, and the session is recorded, so you can check with that later. And I'm going to explain each and every step, and there will be a home assignment with a different system so that you can try it yourself. So now I'm writing down the kinetic energy, and it boils down to the m/2 with the sum of these velocities, horizontal and vertical, squared. And with the horizontal velocity, it is pretty simple because, oh no, not really. So okay, let us look at that in more detail. We have two components of this motion, of this mass. The first component comes from the rotary motion, and the second component comes from the linear motion, right? So let us try to find out what's going on with the angles here. I'm stating that the projection of the rotary motion onto the horizontal axis will be theta dot times L times cosine theta. How come? Why so? Because this thing is just the velocity of the end point. So it's like omega times L, the angular velocity times the length of this thing. And now we're projecting it onto the horizontal axis. And the vertical part, it's the horizontal part. This marker. Horizontal. Going to push harder. And vertical will be theta dot times L times sine theta. Vertical. And also, there's a vertical component that comes from the linear motion of this pivot joint. So here I'm going to first write the simpler component, the horizontal or the x. So I'm going to square it, and it will be theta dot squared L squared cosine theta, well, squared, yeah. And the second is a bit more tricky, but not that much, because here we can write down the sum of theta dot L cosine theta plus just d dot, because it's the linear velocity along the vertical axis. And it is squared, and the brackets are closing. Let's catch up on this. Do you agree, or you don't, or you don't
So
get how did we get here?
So we get the v is equal to basically like v is equal to theta dot L is from like the equations of like rotational motion, right? So basically like omega r. Like
yes, exactly,
Okay.
exactly. So what's going on here is just from the pure rotational motion.
Okay. And for we're just taking the x component of that initially.
Yes, the x component is the horizontal one, so it goes here. It's just being squared, and that's it.
And for the y component, we're taking we're adding the component due to the rotational motion as well as due to the displacement, like the change in displacement
Yes,
from
yes.
Wouldn't it be theta dot L sine theta plus?
Oh, really? Yeah. Yes. Thank you. You're right. You're right. It's my fault. Thanks. Sine theta, and here's d dot. I'm going to write this dot like this one. Yeah. So it's like this. Is it okay?
Yeah, yeah, it makes sense. Yeah.
Awesome. So what can we do? What can we do next? Is we can unwrap the square, or we can skip that. Well, okay. Let's let's take a look at what will happen if we open these braces. Brackets, I mean. So m over 2. Okay. I have expanded those brackets, and here we can notice that these two terms add up to a single term, theta dot squared L squared, because here's cosine squared plus sine squared. So it's m over 2. Here is theta dot square L square plus d dot square plus some cross term, 2d dot theta dot L sine theta. And let us observe this result. What do we get here? Imagine that theta dot is equal to 0. So there is no angular velocity. The mass is just stuck with some angle theta naught. And this rod is moving vertically. So the velocity of the mass is exactly equal to the velocity of this pivot joint. And this is 0. We assume theta dot to be 0. This is 0, this is 0. And we come to the much simplified case of m over 2 d dot square. It makes sense. If there's no rotary motion, this whole system boils down to just mass that is moving up and down. On the other hand, if there is no vertical motion, this system simplifies to a simple pendulum. So d dot is equal to 0, this is 0, this is 0, and this is just the kinetic energy of a simple pendulum, which makes sense again. However, this is a bit of a complication. There is a cross term because of the nature of the system. It's more complex. That's just two things added up. And this cross term becomes more significant, so to say, as the sign of theta increases. Well, you can see the formula. This is the exact formula of the energy, of the kinetic energy of the system. And yeah, are there any questions, or it is clear and it's fine? We can go further. Can we proceed, or is it better to reiterate?
It's clear.
Okay. Okay. We have found the kinetic energy. Now let us find the potential energy. The potential energy consists of two parts. The first part is the potential energy due to the gravitational force. And the second is the energy that is stored in the spring. So I'm going to write it just directly. Okay, so if the zero position, if everything is relaxed, the zero position is d is 0, theta is 0, the pendulum is swinging over here. If the pendulum is moving upward, the potential energy grows. So I'm going to write it down like this. For sure, there will be m times g. And here, we're going to have minus d. Okay, yeah, let it be expanded, right? So d is increasing downwards. So the first part of the potential energy is minus m times g times d. We're going higher along this towards the greater values on this axis, and the potential energy is decreasing. So this is the first term. And the second term will be due to the angle. So if we're not changing the linear displacement and changing the angle, the mass is being uplifted. So there's a second component to that. And it will be m times g times L cosine theta. And let's get the sign. Let's find out the sign. So if the cosine is 1, the potential energy is minimal. And if theta is increasing or decreasing, whatever, if it's changing, the potential energy grows. So as the cosine decreases, the potential energy increases. So there's a minus over here. And we can basically rewrite it as this first part of the potential energy, like minus mg d plus L cosine theta. And the second part of the potential energy will be due to the spring being deformed. And it's much simpler than this because it's just k d square over 2. That's it. Awesome. So we have the kinetic and potential energy. And now we can write down the Lagrangian. The Lagrangian will be equal to, and I'm just copying from here. It's m over 2 theta dot square L square plus d dot square plus 2d dot theta dot L sine theta minus the potential energy. So it's plus mg d plus L cosine theta minus, there's a little addition that didn't fit. So minus k d square over 2. There's a long mass that is dependent on basically everything. It's dependent on the displacement, the derivative of the displacement, angle in nonlinear form, and the derivative of the angle. But this is a full Lagrangian of the system. And if we are now going to insert this Lagrangian into the Euler-Lagrange equations, it will give us the exact equations of motion of this system. And it's awesome. So that's the whole point of us doing that, because we can proceed to using, say, a symbolic representation of Lagrangians and formulas, and we can use libraries like SymPy, which will provide us with automatic tools for differentiating. So this whole Lagrangian formalism could be automatized so much that we can describe a system and do almost nothing by hand with pen and paper for us to get a proper simulation of the system. The proper in terms of the energies being pretty much conserved and so on. So yeah, L by d q sub I dot, and here q1 will be d, q2 will be theta. So I think that we're running out of time. Okay, well, we're 6 minutes late already. After Ramadan, we will have our sessions longer, so we can talk about all the stuff more, and it will be held earlier. It will be held at 6:30. But for Ramadan, we have 1 hour, so for today, we're pretty much done. And what I would ask you to do at home is to derive these equations, 2 of them. And well, you can share them in the chat. You can compare these equations between yourself. Probably they will not match from the first time. You can check for the errors, typos, and so on. They are fine. There's nothing wrong with that. Everybody does that. So you can derive the equations. And next time, we're going to do some programming. We're going to simulate this system. I is 1, 2. Q1 is D. Q2 is theta. And another part of the home assignment that I would ask you to do is to obtain the equations of motion for the cart pole, this one. So it's mass M, pendulum, mass M, angle theta lives here. There's an x-axis, there is 0 somewhere. We have the gravitational field. That's it. So there's another two-dimensional system. It's just like this spring, but it's rotated counterclockwise, and there's a mass instead of the spring. So it's different. However, they share some properties and some intuitions. Is it okay with the assignment? Do you think that you can do that, or not really?
We'll definitely give it a go.
Sure. Okay. Nakia, Nasiba, any comments or problems, or what do you think?
This was really interesting. Thank you. Your explanations are great.
Thanks. Thanks.
Yes, I
Glad to
agree.
hear
Really
that.
interesting. Thank you.
Thank you so much for taking the time to explain everything in detail, by the way. I really
Sure,
appreciate it.
sure. I'm here to do exactly that. So let's catch up next time, and we'll do some programming. We are going to do some visualizations. Those, I believe they will be very nice. So Nivan, John Thomas, welcome to the team. And you can ask the other guys about the offline meeting, who is the other PhD student. So just take a look around and meet the guys. We will meet in person only in summer, I believe, but the rest of the crew are in KU. They're students and employees. Do you know, by the way, Professor Hamad Karki?
No, I don't believe I do.
Okay, so there's a professor, Hamad Karki, and he's he has organized in some sense this team, so he's responsible for the official part and so on. You can talk about the status of this team with him. You can ask what's this thing really about formally, what is going on with the courses, the schedule of competitions. And there is Bushra al-Shahi. She works with him and she's in the chat. So you can ask her as well. Okay, so it's 10 something at KU. That's pretty
I'm
late.
really sorry to ask this so late, but could you pronounce your name in English again? In WhatsApp, it's in Russian.
Ilya.
Ilya.
Ilya, yeah.
Thank you so much.
I think I have to change my name in Zoom because it's not readable. It's in Cyrillic. So thank you. See you next time. And if there are any questions, please write me in direct messages or in the chat. Bye-bye.
Thank you.
Thank you. Have a nice day.
Thank you.
Bye.